All right, in this next section, we're going to take a look at titration curves. Weak acids with a strong base. With weaker acids, the initial pH is higher and pH changes near the equivalence point are more subtle. Weak acids are titrated against a strong base. The initial pH and the pH near the equivalence point are the identifiable features in the curves. So you can see our initial pHs, and then in the vertical sections, the pH at the equivalence point. An increase in the initial pH indicates that all acids except the one with the red curve right here are weak acids. See how we see a slight increase in the initial pH? They all have the same concentrations as the volume of the titrant base is the same in all cases. Let's take a look at a couple of curves for weak and strong bases with a strong acid. So in black is the titration of a strong base with a strong acid. It has an equivalence point at a pH of 7. In blue is the weak base being titrated with a strong acid, and it has an equivalence point less than 7. In this case, methyl red is the indicator of choice because the pKa is near the pH at the equivalence point. Analyzing a titration curve. Use the titration curve to identify the volume and pH of the equivalence point and half equivalence point. The curve indicates that the titration occurring is between NaOH, a strong base, and a weak acid, as the pH starts at 3 on the curve. The acid is monoprotic as it has one S curve in the plot. In other words, we just have the one equivalence point for the neutralization of the monoprotic acid. The volume at the half equivalence point is always half the volume at the equivalence point. So here, if this is my equivalence point at a pH of 8.5, after a volume of 25 milliliters have been added, the half equivalence point then occurs after 12.5 milliliters is added, and at that point the pH is 4.1. On the other hand, the pH of the half equivalence point is not generally half the pH of the equivalence point. So even though the volume is exactly half, the pH is not. So that just means you need to read the pH from the graph. The pH at the equivalence point is not 7. As it's a weak acid, strong base titration, the pH is slightly above 7. So the salt that's produced has the conjugate base ion of the acid, which will undergo hydrolysis and produce more hydroxide ions, making the solution slightly basic at the equivalence point, which is why we get that pH slightly above 7. So here's what the hydrolysis looks like. We have the conjugate base of the weak acid present in the solution at the equivalence point. In water, it produces the weak acid and excess hydroxide ions, and there's an equilibrium established here that we can use in order to calculate the pH at the equivalence point if necessary. We did that in the previous section. If you know the pH from the curve, you can determine the Ka of the acid using this derivation of the Henderson-Hasselbalch equation. A suitable indicator would be the one with a pKa value close to the pH of the endpoint. The best buffering zone or buffering region is at the half equivalence point, because at this point the changes in pH are much more subtle. And that's because you have a buffered solution of whatever the weak acid is in this case and its conjugate base. Prior to the half equivalence point, so over here, there will be less of the conjugate base and more of the acid. So the ratio of A minus to HA will be less than 1 because this concentration is greater. So the log term will be negative. So this ends up pKa minus. So the pH will be less than pKa. At the half equivalence point, these two concentrations are the same. And so this log term is 0 and pH is equal to pKa. After the half equivalence point, we will always have more of the conjugate base than we have acid. So this ratio will always be greater than 1 and the log term will be positive. So we're adding to the pKa. So pH will always be greater than pKa. Titration of diprotic acids. So a diprotic acid has 2 protons that can dissociate, right? And each proton dissociation step and the corresponding neutralization is represented by what we call an S-curve. So this is early in the neutralization, at the equivalence point, and after for each neutralization of each proton. Here are some important points on this curve. At 5 milliliters, A represents the first half neutralization point. At 10 milliliters, B represents the neutralization point corresponding to the first proton dissociation. At 15 milliliters, C represents the second half neutralization point, or the second proton. And at 20 milliliters, D represents the neutralization point corresponding to the second proton dissociation step. All right, so in blue, let's zoom in. A represents the first half neutralization point. At this point, 1/2 of the amount of the available first dissociation protons are neutralized, and pH is equal to pKa1. A is the best buffering region where there are equal amounts of the acid H2A and the conjugate HA- to resist pH change. B represents the first proton dissociation and the corresponding neutralization. C represents the second half neutralization. It is the second buffering region where the acid HA and conjugate A2- are in equal amounts, where pH is equal to pKa2. D represents the second neutralization point. The major components in the solution between points B and C is HA1 -1, okay, and between points C and D is A2-. This curve represents a triprotic acid titrated against a strong base NaOH, indicating 3 distinct S portions. Here's 1, 2, and 3, corresponding to the 3 different neutralization points, the equivalent point for the first, the second, and the third, and then labeled their half equivalence points as well.